Hello everybody. This small movie contains supplementary information to the blogger's post under the title Buckling Length of a Column with a Variable Cross Section. In my opinion, it is a very good post which increases the knowledge of the practicing engineers, and it is showing that linear buckling analysis can be a very efficient tool in everyday work. From that post, the engineer can obtain three ideas or assumptions, of course, in my opinion. That linear buckling analysis can be useful for everyday work, which is excellent, great, and very good. The second assumption is that engineer doesn't need the effective length when is dealing with flexural buckling, and it is true. He can obtain critical force from the alpha critical parameter calculated in linear buckling analysis, then multiplied it by the applied force in the structure. Then he will obtain n critical, which put in the formula for slenderness. So he will get the slenderness without dealing with effective length. There is more. If the engineer is using general method implemented in the Eurocode in the section 6.3.4, there is no need to use critical force at all. All what is needed are two parameters described in the Eurocode as alpha ultimate and alpha critical. And from these two parameters, he can obtain the slenderness. There is even more. There is no need to use critical moment or bending moment. If the engineer is using for the linear analysis, buckling analysis, the 7 degrees of freedom finite bar element or shells or finite strip method. Therefore, the alpha critical will contain all the global buckling modes, flexural, torsional, and lateral torsional buckling, or complex one. And then the alpha critical is reliable and can be used for obtaining the slenderness. The last but not least, in my opinion, is the third assumption. An engineer can think that the calculated buckling mode for the upper part of the column is relevant as well for the lower part of the column, which is not true in that example. It has to be said very clear and very loud. The alpha critical relevant for the upper part of the column doesn't equal for the lower part of the column. Therefore, the effective length can be calculated using this critical force for the lower part. It will be proved in a moment. So it is a conservative approach and can be disturbing when an engineer will try to dive a little deeper into the stability problems. Now example and proof. To prove it, I have slightly changed the initial conditions. I changed the support from pinned to fixed, and then I changed slightly cross sections of the parts of the column. So what we have, it is a example from the post of the blogger. We have here 100 kilonewtons a load, and I will perform now the analyzing. Now we have a buckling which is 19.19 alpha critical. This is the first mode. If we multiplied it by the applied loads, then we have 1919. So it is up to now, it is almost similar critical load to the calculated by the blogger. And when I will perform the analyzing, the alpha critical has become very close to 1, which means that the structure is loaded by the critical load. But as I mentioned, I slightly changed the initial conditions. You can see there is a support which is fixed. At the other end is normal pin support, and also I slightly changed the sections, and it is also loaded by some load. And when I perform the analyzing and go to the buckling, we can clearly see that this mode is relevant only to the upper part of the column. There is no change in the lower one. Therefore, you shouldn't use that buckling values to the lower column. This is 4.9, it is a bar. I also did that for the shells. We can see here the shells, and when I perform the buckling, we have 4.9, the same situation, and the same situation, there is no move at all. That's why we shouldn't use the first value for the lower column. We can, but we have to be aware that this will be on the conservative side, and I will prove it. Now, I load the structure by its ultimate load, which is almost 920 kilonewtons. And now I perform the analysis. I will check the sections, but only sections. Okay, member check, I will delete. Okay, there is the global checks, upper, this is the cross-section checks is 74%, lower is 21.8. Now I will go to the global checks. I will add. So this is the upper column selected. I will select it, go next, and we'll put the critical load, and now I will check it. It is 101%. It is okay. Then I will do it for the lower column. Next. And as well, I will do it for that column 99. Next. And what we have is 58% of utilization. So that the utilization which was proposed by the blogger. And what we have now, I also performed buckling sensitivity. Buckling sensitivity in Consteel is indicating the relevant buckling for the relevant buckling mode for the particular bar based on the energetic comparison. So now we have for the upper column 2.12 and for the lower column 32 alpha critical. Let's go to this alpha critical. Jump to this figure and go to the buckling. This is the third load, the third buckling mode, and we have here a nice curvature of that bar. And this is the buckling relevant to this lower part. I know what's the critical load of that for that part. It's 12,520 about. We'll go back to the global checks, to the member checks, sorry. We'll select it and go again. And now we put here this critical load. Okay, next. And we'll check. And this is the utilization which is relevant for that lower part of the column. Okay, so now I've made some comparison of the utilization. Here we have the reduction factor method, and we have the upper column, lower column, and now we have the classical approach where I have here 1919 critical load and the lower part of the column, which is 12,521, and here is 100 utilization, here is 24.4. For general method, if you use 6.3.4 section of the Eurocode, you get almost the same values. What has proposed a blogger? It is for the lower column 57% and for the upper column 61%. 57, and in general method, if I will use this alpha critical, it will be 61%. There is even more in that post. Let's see. In LinkedIn, under the announcement of that post, there was a comment made by Vasilis Reksinas, and he has a problem with imperfection method. An engineer has made the same example as I performed and as the blogger has introduced in his post, and as well as the blogger, he has calculated the critical force, then he has calculated the ultimate load based on the classical approach, and he has started to calculate it with the imperfection method, but the imperfection was described by the not local ball, but here is according to by the relevant mode. I suppose it was the first mode, and he was using the amplitude from the table 5 for the curve B plastic for plastic analysis, which is 1 divided by 200, and he has got the result of the ultimate load in that imperfect system structure at the level 656 kilonewtons. And to get the ultimate load obtained by the classical method, he has to use the amplitude which was at the level of L60s, not L20 to 200s. So he would like to know what the proper initial deformation for nonlinear analysis. He was using the third order theory. In my opinion, for that example, there's no need to use third order big deflection theory, but let's leave that. The problem here is that it is the table 5, which is very conservative and in generally the utilization will be much higher than in the classical approach, general method, or other imperfections. So this is very conservative. I don't know why it was maybe why it was implemented like that. Probably there haven't been a better method for the engineers to get them just to the very first estimation of the level of the utilization. And most of the engineers, the imperfection method knows from that side, from that table and that equivalent sway imperfection and that bow imperfection. But in the Eurocode is also implemented very powerful method which was developed by Hladny and Stuberova, and it is in the chapter 5.2.3, I think, point 1.2. I don't know. I have to check just a moment. I don't remember. That was 5.3 and 11 here. Here it is. And as I mentioned, the author of that method is Eugen Hladny, Magdalena Stuberova. But it has been noted that it is valid only where is in the member where is present only decompression, nothing more. If there will be a bending moment and a torsional, lateral torsional buckling present, so it will give unreliable amplitudes and it can't be used there. But in our example, it could be used. As well, there is a lately developed the imperfection method, which is called overall imperfection method, and the authors of that methods are Joseph Chalet and Ferenc Papp. And I will also use that imperfection method to see what's going on in our example. I will perform the analysis, okay, and I will apply the eigen shape as an imperfection and calculate the amplitude by the Hladny's method, which is implemented in the Eurocode. Okay? Then I will check the amplitude. It is here. Now I calculate the first, second, and buckling analysis, made a calculation, and we'll go to global check and check only these sections. And as you can see, we have the utilization of the upper column at the level of 97 and the lower column at the level at 23.5%. Okay, so I will delete it. And I will perform another method, which is called overall imperfection method for the calculating the amplitude. And we can see that the amplitude here is at the same level as it was provided by the Hladny's method. It is 13.4 millimeters. There's no sense to calculate it again, but I will do it just to prove that it works. I will go to global check, apply, made a calculation, and we see that there is 97.2 and 23.5 utilization. Now I'll go back and delete that imperfection. I will make the imperfection from the table 5 but on the shape provided by the by eigenvalue. So we apply the imperfection based on the eigenvalue, but with the amplitude provided by the table 5. Okay, we can make the calculation and check. And as you can see, as everybody can see, the utilization is 140 for the upper column, which is very conservative, and for the lower column, almost 26. Okay. But someone can say that it haven't been provided by the bow imperfection, which is half sine wave, and it is not proper, and so on. So I have prepared as well that example. So we have here a deformed shape. One is undeformed, and the second is deformed by the factor of by the amplitude, which is 32, and it is 1 of 250 of the height. So we can now make the analysis. Of course, the load is, as you can see, the ultimate for that column, and go to the global check, and in the global check we only checking the, and we have here as well slightly lower 132 the utilization, but still it is higher than it should be. Okay, now we can I've made some comparison of the methods. We can see the reduction factors based on the classical approach, then general method, and then for the lower column proposed by the blogger, the way of obtaining the effective length or critical force, which is extremely conservative. And then we have the imperfection method based on the Chladni approach, then based on the Papp-Chalet approach, which is called the overall imperfection method. We can see that in that case, in that example, the results are exactly the same. And here we have two examples of the checks which was provided by imperfection method, but with the amplitude calculated from table 5.1. It is buckling, and the shape was provided by buckling mode. Here was provided by half sine wave, and you can clearly see that 13.4 millimeters divided by 8,000 millimeters height is almost 1 of the 600ths, which is exactly the same what has had to do the engineer to obtain that ultimate load in the elastoplastic analysis using the third theory and linear buckling analysis shaped to deform the column. Okay, so there is that problem with the imperfection has been already introduced on the Consteel blog. It is the first article. This is the second one. You can see the table. You can see the comparison of the methods, and I invite you to read it, to learn, to see what's what's going on in new Eurocodes. So at the end, we can summarize that general method and overall imperfection method can cope with different shapes and of the structures, and as well with different shapes of the sections. So that's, I think, the end of this short summarization and supplementary information to the blog post. Thank you for your attention. Everyone could see that the simple example is still very interesting. Again, thank you very much, and till the next time.